Welcome, everybody, to our Math 60 video lecture. We'll cover 4.1 and maybe 4.2 today. So section 4.1 is Introduction to Expressions. So what is an expression? An expression is a mathematical sentence. And we know that most of the time sentences have nouns, verbs, and grammar. Sometimes they have adjectives and other parts of speech, etc. But I'll be able to kind of talk about everything here using just nouns and verbs and grammar. So in math, mathematical nouns are numbers and variables, like the number 3 or the number -7 or the number 1/2 or the variable x or a combined variable like 5x. And these are our mathematical nouns. Mathematical verbs are the operations like addition, subtraction, multiplication, division, and eventually we'll add others, right? Like we have talked about powers, right? Exponential notation, square roots, as you move on, functions in general. And then mathematical grammar this is basically the order of operations. This is one reason we spent time learning the order of operations, so that when we develop our expressions, we do them in the right order. And the other piece of mathematical grammar are equal signs and inequality signs. So when you hear someone talk about a mathematical expression or an expression in general, they're talking about a mathematical sentence with nouns, verbs, and some kind of grammar, which tells you how to combine the nouns and the verbs. I'm not an English teacher, but my mom was for many years. And that's my understanding is like grammar is how you combine these things so that they make sense to yourself and to other people. So let me give you some examples. Two plus 3, that's a mathematical expression because it has some nouns. It's got the 2 and the 3, and it has a verb. And the grammar says, well, if 2 plus 3, you combine them generally. I don't have to say what that equals. That is, in fact, a mathematical expression. I could write it with an equal sign. That's also a mathematical expression. You get super simple. The number 0 is a mathematical sentence. It's a number, it's a noun. If you if you are talking to someone and they're going too fast, what might you say? Yeah, slow down or wait, right? Single word, still a sentence. Okay. And then we can have some of our more complicated ones, like -1/7 plus 2/3 equals my brain's moving a little slow today, but that's going to be 14/21 and 3/21. So it's going to be end up being 11/21. Right, so still a mathematical sentence, still an expression, but significantly more complicated. And one of the parts about this section is introducing significantly more complicated expressions to solve beyond what we did in chapter 3 or before. So if we're working with more complicated expressions, there's basically 3 steps for working with complicated expressions. The first one is identify the nouns, i.e. the numbers and or variables. That's one of the light fixtures, in case you can hear it online or on the video. Hopefully, facilities is going to come in and work on the projector in the next day or so. Hopefully they'll fix the light as well. So identify the nouns, identify the verbs, i.e. the operations, and then use a grammar, which is order of operations and or equal or inequality signs to evaluate or solve the expression. All right, so let's do 2 simple examples and then some complicated examples. In fact, let's do the -1/7 plus the 2/3. And I want to evaluate that expression, right? Combine those terms together and make it simpler. So my nouns, my numbers are -1/7 and 2/3. My order of, or my operations are addition. And my goal is to evaluate, right? To see what they are when I add them together. And this gives me information about how to solve it. So I'm working with fractions and I'm adding them. And so I find the section in my notes or in the textbook that tells me how to add fractions, especially when they don't share the same denominator. So in that case, I would find what's missing from each. The 1/7 is missing a 3, and the 2/3 is missing a 7. And I get -3/21 plus 14/21. And I put those together as soon as they have the same denominator. You see how we're using our grammar here? Our grammar lets us change fractions with different denominators into fractions with the same denominator. And then we can add them together and we get 11 over 21. And now let's solve the equation 3x plus 2 equals 14. The first step, we identify the nouns. That you might kind of do that in your head. That's okay. But it's all right to be really explicit. I've got a 3x, a 2, and a 14. Those are the objects that I'm working with. Here I've got an addition and a multiplication because it's the 3x. And since I want to solve, I need to undo my operations in reverse order. That's my grammar. It reminds me, how do I solve an equation? I have to undo my operations in reverse order. And so now that we have seen what we're trying to do, you can find the section in your book that shows you how to solve multi-step equations, or look up in your notes, or practice it enough so that you remind yourself of the steps. And first we want to isolate the x, so we'll subtract 2 from both sides and get 3x equals 12. And then divide both sides by 3 to get x all by itself, and we get x equals 4. So those were both review, because we've done things like those before. On your worksheet and your homework, you're going to get a little bit of review, but you'll also get some new ones. So here's a new one. Let's evaluate 3/5 plus 1/3 times 6/5. So my nouns are, well, I'm working with fractions. I won't write them again this time because, well, I will. I should. 3/5, 1/3, and 6/5. And the operations are addition and multiplication. But since I'm evaluating, I need to use my order of operations. Which means I do the fraction multiplication first. Right, so we've done fraction addition and we've done fraction multiplication. We just haven't combined them in the same expression. But if I follow the fact that 3/5, 1/3, and 6/5, they're all numbers. And so PEMDAS still applies even though they're fractions. So the 3/5 is going to wait over here while I do the multiplication, because multiplication comes before addition in PEMDAS. And I know when I multiply fractions, I multiply the top and I multiply the bottom. And now that I've done the multiplication, I'm back to adding fractions. And since 5 multiplies to be 15, I just need to multiply the 3/5 by the missing piece, which is 3. And I get 9 over 15 plus 6 over 15, which equals 15 over 15, which is 1. So 3/5 plus 1/3 times 6/5 is actually equal to 1. course, I didn't know that when I started this. The biggest challenge in my mind about these expressions is as they start throwing more numbers, as your sentences get bigger, and then they use more operations, it becomes more and more complex to keep track of what to do when. And so that's what you really need to practice. And that's why going kind of slowly and systematically can help. So here's another example from the book. Let's evaluate -2 squared plus 3 plus -3 in parentheses plus 4. I'm going to do not plus 4. I don't think I want to do plus 4. I'm going to do plus 5. So it's not quite from the book. Times the quantity 4, or sorry, divided by the quantity 4 minus 5 times the quantity -2 minus 7. So it's probably too much to just write down all the numbers that you see in terms of your nouns, right? Like if I wrote 2 and 2 and 3 minus 3 and 5 and 4 minus 5 minus 2 minus 7, that would just be overwhelming. So I'm going to identify the types of functions. They're all integers, or the types of numbers. They're all integers, positive and negative. And so that's going to remind me that I need to remember how to add and subtract and do powers of positive and negative integers. Fortunately, I'm not really going to have to work with fractions this time. I mean, fortunately. And then in terms of order of operations, I've got a power. I've got some addition, some subtraction, and some multiplication and some division. So I've got a whole bunch of different operations here that I'm going to have to keep track of. And since I'm evaluating, I need to do PEMDAS, keeping in mind that it's not really just PEMDAS, but it's also remembering when you do PEMDAS, you do the top and the bottom separately before you worry about combining them. So it's really put to PEMDAS. So here we go. -2 squared plus 3 plus -3 in parentheses plus 5, all divided by 4 minus 5 times -2 minus 7. And as you get more comfortable, you may kind of combine some of these steps. You might start taking care of the top and start taking care of the bottom. But I just want to do this really systematically first. So we're just going to take care of things in the parentheses. So the -2 squared is going to stay. The +3 is going to stay. Plus a -3, let's bust that parentheses open and just write it as a -3. And then a +5. And on the bottom, let's take care of what's in the parentheses too. So 4 minus 5 is -1. -2 minus 7 is going to be -9. Okay. Now taking care of the top and the bottom separately, Let's take care of the top first, and we have something to a power, so we're gonna evaluate that first. Now remember, the minus sign out front means you do the power and then you apply the negative. So it's gonna be -4 plus 3 minus 3 plus 5 on the top. And -1 times -9 is +9 on the bottom. So we've taken care of the exponential in the top. We've taken care of the multiplication in the bottom. So now we need to do the addition and the subtraction in the top while we leave the bottom alone. -4 plus 3 is -1. Working left to right. And you might say, well, I'll take the +3 and the -3 and those cancel, and that would be okay. But if you want to do that way, that's fine. But I'm going to work really systematically, right? Right, the multiplication division works left to right, as does addition and subtraction. So -4 plus 3 is -1. -3 -1 plus 5. Sorry, -1 -3 plus 5 over 9, which is -4 plus 5 over 9, which is 1 over 9. And that's as far as I'll go. I'm happy to leave it as a fraction. This is an order of magnitude more complicated than anything we've done so far. And it doesn't involve fractions yet. But if it did, we could handle it. But there's not an example of that with fractions that you're asked to do. I guess there is. Your worksheet has a simpler one involving fractions. The truth is, you don't often have to evaluate something this complicated, let alone this complicated with fractions. So these challenge questions are to practice really working through those steps systematically, but you don't encounter them super often in the wild in math. All right, that's our first mini topic from 4.1. 4.1 is actually 3 mini topics. It's first one is how do you evaluate more complicated expressions? The second mini topic, and this is something that you get to come back to again and again in Math 70 and 95, is scientific notation. And to be honest, I can't remember if we've done this yet or if it was something I did in a Math 70 video. I don't think we've done this yet. Writing big numbers shorter. But before we get to that, let's talk about significant digits. Or sorry, significant figures is the word the book uses. And I'm just going to start a new page. I feel like starting a new page. Significant figures and scientific notation. So, what's the difference between 29K and 29,000? Say that again?
The way it's worded.
The way it's worded, sorry. Yeah, we often say 29K and actually we mean 29,000 is just kind of a fast way. And you may have not done that so far, but K stands for thousand in Latin, kilo, like kilometer or kilogram. And so often instead of saying 29,000, we just say 29K because it's a shorter way to write it. What is the difference between 29K and 29,003? Three. If you were to subtract them, the difference would be three. That's true. What I'm going to say is precision. If you have $29,000 and I have $29,003, there's a cup of coffee, right? It's really the same, but it's about the precision. 29,003 is a very precise number. 29K or 29,000 with three zeros is probably a good enough estimate. So significant figures the number of significant figures tell you how precise the number is. And actually, I want to change this. I don't want the zeros here. I actually want that to be the 29K. $29,003 has 5 significant figures. Because in order to get the full precision, you need all 5 of those numbers. There are 5 important numbers that tell you the value. $29K has 2 significant figures. Because only 2 numbers give you an idea of the value. So the way we write 29K as a full number with 2 significant digits is we say 29,000 to 2 significant figures. Means the 29 matters, but the 3 zeros could be other numbers. We just can't tell. These three numbers are all the same. Not these ones, the ones I'm going to write. 29,000 to two significant figures. 29,002. Let me do 5 just so I don't use the same numbers all the time. To suit two significant figures. And 29,181 to two significant figures. All three of those numbers might as well be written as 29,000. Because the numbers that we are useful for figuring out the value are only the first two. And the other numbers, in this case, 3 zeros, in this case, 005, in this case, 181, those really could be anything. Right? You could think about it as measurement error. If you're weighing an elephant, a whale, maybe a whale, right, in kilograms, could be 29,000 kilograms. It could be 29,005 kilograms, but maybe it just ate a salmon, right? Big salmon. Could be 29,181 kilograms, but it's got a bunch of barnacles on there that you'd have to scrape off, right? So it's measurement error. Now, sometimes this really matters. Significant figures can matter, but that is usually a human choice. Here's a good example. The New York Marathon just happened yesterday. All right. The New York Marathon happened yesterday. And the winner of the women's marathon was Helen Obiri with a time of, I'm going to convert to minutes. Sorry, convert to hours. Oh, that's so weird though. Okay. Well, this is not a good example. Let me see. Awesome. That's what I wanted to see. Cool. Yeah, this is a great one. All right. Where are their first names? Benson, Kipruto. Nothing wrong with the women's race. It's just the numbers are not working out quite as how I want it. So Benson, Kipruto had a time of 2 hours, 8 minutes, 9 seconds. So let's just call it 2 hours. If we only care about hours, right? If we count the minutes and seconds as insignificant, that's a super fast time. But the second place finisher, Alexander Mutiso, also had a time of 2 hours. If we only care about hours. But if we extend our significant figures into minutes, technically it was 2 hours and 8 minutes. If we care about minutes also. Is that enough to say who won? No, because they still seem tied if all we care about is minutes. So now we have to care about seconds as well. Actually, Alexander Mutiso finished in 2 hours, 8 minutes, and 9 seconds. If we care down to the second. And that's actually what this newspaper article reports. It only reports it to seconds. So according to this news article, what happened to the New York Marathon? They tied, but that's not true. Here's a picture. Sorry. There's Benson Caputo on the left. So Benson Caputo won by, I'm going to have to make this up because they don't tell. Actually, they probably have it. Let's see. No, they literally listed it to the second. I guess they don't keep track, but the photo finish showed you who won. Right, but that, I mean, that actually for me illustrates really well the importance of choosing your significant figures. Because our first place winner had the same time as a second place winner because they only record down to the second in terms of significant figures. But to decide the actual winner, this is going to be like 9.3 seconds, and this is going to be like 9.8 seconds. Okay. So that's significant figures. Now let's talk about scientific notation. Which is collapsing large numbers into a compact form. So if I have a really big number like 176,293,428, that can be a lot to carry around. And in fact, not all of these figures, not all of these digits may be significant. Right? Maybe my level of precision for measuring can't get me down to the ones digit. Maybe it only can get me down to like the 100,000th digit. So it may be basically the same as 176,200,000. And again, that's a human decision. I feel like my measurement is only precise to 4 significant digits. Or 4 significant figures. So scientific notation replaces the zeros with powers of 10. So how I do it is pretty simple. I imagine there's a decimal point at the end of my number, and I count how many zeros I need to get rid of them. And then actually I keep going. So I count 1, 2, 3, 4, 5, 6, 7, 8. I go all the way until there's only one number to the left of the decimal. Step the decimal left until there is only one number left of the decimal. And then count the number of steps. There were 8 steps. So I rewrite my number as 1.762. I get to toss away all those extra zeros because they're not significant anymore. And then I multiply it by 10 to the 8th because I took 8 steps. Let's do another example. Let's look at 19,312 with 3 significant figures. So the 1, the 9, and the 3, I'm confident, but the last 12, that could be measurement error. So I'm going to write my scientific notation by taking the decimal point that I imagine here and moving it 1, 2, 3, 4 steps. And so I have 1.93 times 10 to the 4th. Because 19,312 with 3 significant figures, as far as I can tell, is 19,300. Let's do another example. Let's do, let's see, 221,007 with 5 significant figures. This one's going to be a little different. So I've got 5 significant figures, 1, 2, 3, 4, 5. So actually, not only the 221, but also the first 2 zeros are significant. Right, those first 5 digits are all significant. It's only the last 7. It could be more, could be less. So if I want to write it as scientific notation, again, I move the decimal 1, 2, 3. That comma gets in my way. That's why I usually don't write commas. It confuses me. 1, 2, 3, 4, 5.
Does it always move to the tens place?
It always moves so that you have a single number to the left. Yeah. So 5 steps. So I write my number and I make sure that I have 5 significant figures, 2.2100 times 10 to the 5th. I need those zeros because that's precision. Right. And that's the difference between declaring Caputo the winner and saying it's a tie. Right, is having those extra little pieces of information. I know that I've measured precisely enough that the only thing that could be wrong is the 7. The 0 and the hundreds and the 0 and the 10 are correct. The only thing that could be wrong is a 7, so I drop that. All right, that wraps up the second of our little mini topics. And the third of our mini topics are algebraic expressions and formulas. So an algebraic expression is just a mathematical expression. It's a mathematical expression that includes variables. Like 3x plus 2 equals 14. That's an algebraic expression because it includes a variable x. Or something different like 20xy. No equal sign there, but it's still a mathematical sentence and it has variables. Formulas are expressions that are used to represent specific, I'm going to say situations. Like the area of a rectangle. And this is nice because we've actually done this before when we were multiplying. But if I want the area of a rectangle that's length 3 on one side and length 5 on the other, I know that there are 15 little squares in there. And in general, an area that has a specific width and a specific length, I write my L's like this so they don't look like ones. You don't have to, but that's what an L looks like when I write mathematically. And that's not how I write it when I write it in words. I make a vertical line. So mathematically, my L's look kind of, they make the little cursive. So the area of a rectangle is length times width, right? It's a mathematical expression that represents a specific situation. And by putting in different numbers for the length and different numbers for the width, we can find the area of different rectangles. So what's the area of a rectangle where the length is 19 and the width is 2? What is that area?
38.
38. Because 38 equals 19 times 2 equals length times width. Okay. Another common formula, again for area, is the area of a triangle. The area of a triangle is 1/2 times the base times the height of the triangle. So 1/2 times B times H. And the reason for that is if the base of my triangle is B and the height is H, I could imagine that I form a rectangle. The area of a rectangle would then be B times H. So the area of the triangle is half of that. And that actually works whether or not your height is completely vertical, right? Whether or not the vertical leg of the triangle is perpendicular. This is called a right angle. I don't know why they use the right angle. I might have called it a square angle, but anyway. And it still works even if your triangle has a different shape, as long as you know the base. Let's say the base here is 10, and the height is from the base to the tallest point. Let's say the height is 4. Area is still 1/2 times base times height, which is going to be 1/2 times 10 times 4, which works out to be 20. And it even works if your triangle kind of leans over to the side. Because there's still a height that you can think about.
How can you put that in a calculator, 1/2?
So you could do a 1/2 fraction. You could also use 0.5. So 1/2 times base times height. In this case is 1/2 times 5 times 3, which is 15/2, or if you want it as a decimal, is 7.5. And yeah, the 1/2 times base times height, you could do 0.5 times the base times the height. Or you could do the base times the height and then divide the whole thing by 2. That all works for your calculator. Those are mathematically equivalent. So these simple expressions are formulas because you use the formula with new numbers whenever you want to evaluate it for a new shape. Right? It's a mathematical expression used in these specific situations, but it's flexible enough to use in different situations. All right, let me give you another example. Let me take a rectangle where the width equals 7, the length equals 12, but I'm going to carve out of that a triangle where the base equals 9 and the height equals 4. So I want the area of this funky shaded polygon. Well, to do that, I'm going to break this more complicated problem into simpler pieces. I'm gonna find the area of the rectangle. And I'm gonna take away the area of the triangle. Because that will allow me to find the area of the shaded polygon. And I use my formulas for the area of the rectangle, length times width, minus 1/2 base times height. So it's going to be 12 times 7. I'll put those in parentheses to remember. That's my rectangle. And then I'm going to take away 1/2 times the base, which is 9, times a height, which is 4. And now I'm back to what we were doing at the beginning of today's class. I'm doing a more complicated algebraic expression where I have to say, okay, I've got a bunch of numbers, some of them are fractions, and I have some multiplication and some subtraction. And I'm evaluating, so I'm going to do the multiplications first. So 12 times 7 is 84. 1/2 times 9 is 9/2 times 4. I'm going to have to come over here to finish it. 84. 9/2 times 4 is 36/2, which simplifies to 18. And 84 minus 18 is 66. So the area of this shaded polygon is 66. All right, because this was 3 different ideas, it actually took a lot of time to go through. So I'll stop the video here. Thanks for watching.